All right, let's kick things off with a quick mental challenge. Think of any three consecutive square numbers. Let's start with something really simple, like 1, 4, and 9. Now, what happens if you add the smallest and the largest of those squares together, and then subtract twice the middle square from your total? Go ahead, you can actually just do the math right in your head.
Got your answer? Okay, let's walk through it. First, we add the 1 and the 9, which obviously gives us 10. Next, we need to subtract twice the middle square. Well, our middle square is 4, so 2 times 4 is 8. 10 minus 8 equals 2. Now, here's the really wild part. This isn't just some lucky coincidence. If you try this with way larger consecutive squares, say 25, 36, and 49, you do the exact same process. 25 plus 49 minus 2 times 36. The result? Magically, it is absolutely always 2. No way, right?
So, that little math trick might seem super mysterious, but it's actually just our very first glimpse into an incredibly powerful secret mathematical language. Welcome to our masterclass on demystifying algebraic identities. Think of this explainer as your essential survival guide for grade 9 algebra. We're going to decode these surprising numerical patterns, and by the time we're done, you'll know exactly why tricks like the one we just did work every single time.
Here's our game plan for today. First, the magic math trick we just did. Second, visualizing algebraic identities. Third, the essential core identities. Fourth, expanding to cubes. Fifth, a quick pause, solve, and recap. And finally, number 6, the ultimate exam formula sheet.
So, diving right in. Part 1, the magic math trick.
Returning to that trick, we noticed a pattern that was universally true. And that means we're dealing with identities, not just your basic equations. The crucial difference here is this. An equation is kind of like a padlock with a very specific key. Take x squared minus 1 equals 24. That statement is only true if x is exactly 5 or negative 5. Anything else, and the lock stays shut. But an identity is a master key. It's a mathematical rule that is true for absolutely all values of the variables inside it. It doesn't matter if your x is 2, 2 million, or negative 50. An identity always holds true.
Moving on to Part 2, visualizing algebraic identities.
I know memorizing a bunch of random letters can feel pretty tedious, but here's the thing. Identities aren't just abstract floating symbols. They actually represent real, physical geometric spaces. Imagine a large square. Its sides are built by combining two lengths. Let's call them A and B. So the total area of this big square is A plus B all squared. But look at how that area is constructed on the inside. The total space is made by adding together a large yellow square, which is A squared, a small pink square, which is B squared, and two green rectangles, which each have an area of A times B. Put all of that together visually, and you get the famous identity. A plus B squared equals A squared plus 2AB plus B squared. It's literally just geometry in action.
All right, Part 3, the essential core identities.
To quickly recap, we just saw that algebraic identities are simply geometric areas translated into math, and translating that visual geometry into algebra gives us our fundamental toolkit. I call these the core 4 identities. These are the absolute essentials you need for simplifying calculations. We've got our standard square, our difference of squares, and the trinomial square. I highly recommend getting super familiar with these 4 lines. They really are the bread and butter of grade 9 algebraic manipulation. But hey, I did promise you some shortcuts, didn't I?
If staring at a giant list of formulas stresses you out, just remember this golden exam rule. You honestly don't even need to memorize the second formula if you already know the first one. To get the subtraction identity, literally all you do is replace the positive b with a negative b in your addition identity. Because a negative times a negative is a positive, the b squared at the very end stays positive. But that middle term, that flips to negative 2ab. It's a fantastic little shortcut, and it really saves brain space during a stressful test.
Let's kick things up a notch. Part 4. Expanding to cubes. Okay, so we've mastered two-dimensional squares. Now let's escalate to 3 dimensions with cubic identities. At first glance, I know, these look super long and intimidating. It's like alphabet soup. But don't panic. Just like our squares, these follow a really beautiful, predictable pattern. For a plus b cubed, notice how the powers of a go down, 3, 2, 1, while the powers of b go up. And for x cubed minus y cubed, notice how we just pull out that common factor of x minus y right at the very beginning. Recognizing these patterns is the real key here.
Let's actually see this in action with a highly complex exam-level question. Look at this monster expression, 8n cubed minus 60n squared m plus 150m squared minus 125m cubed. On a test, that looks absolutely terrifying. But watch how easily we can break it down. Step 1. Look at the ends. 8n cubed is just the cube of 2n, and 125m cubed is just the cube of 5m. Boom! We just found our a and our b. Step 2. We check those messy middle terms to see if they fit our pattern of 3a squared b and 3ab squared. And guess what? They do perfectly. So this whole massive, scary polynomial just collapses beautifully into a simple factored form, 2n minus 5m all cubed. That right there is the magic of identities.
Which brings us to part 5. Pause, solve, and recap.
Okay, I've been doing a ton of talking, so now it is your turn to actively apply this stuff. I want you to evaluate the square of 117. But here's the catch. No calculators allowed, and no standard long multiplication either. You have to use an algebraic identity to solve it. So grab a piece of scrap paper, pause this explainer right now, and give it a shot. Don't worry, I'll be right here when you're ready.
All right, welcome back. Let's see how you did. The big trick here was realizing that 117 is just 100 plus 17. By making that one tiny change, we can use our very first core identity. We substitute the numbers to get 100 squared plus 2 times 100 times 17 plus 17 squared. And suddenly, these are numbers we can actually calculate in our heads. 10,000 plus 3,400 plus 289 gives us 13,689. This is exactly why we use identities in real life, guys. It makes mental math so much faster and way less prone to simple errors.
And finally, part 6, the ultimate exam formula sheet.
We are in the home stretch here. But before I give you your final study tool, I have to issue a massive warning about the single most common trap students fall into. Listen closely. A plus b squared is not equal to a squared plus b squared. I know when you're rushing during an exam, it is so incredibly tempting to just distribute that exponent. But think back to the visual geometry we did earlier. If you leave out that middle 2ab term, you are literally erasing those two green rectangles from existence. Don't throw away easy points. Always, always remember the rectangles.
And here we are, the whole shebang, the ultimate identity cheat sheet. You've got your basic squares, difference of squares, trinomials, and all your cubic formulas in one handy spot. I highly recommend taking a quick screenshot right now. To wrap things up today, remember that identities are universal patterns. They represent physical geometry, and recognizing them is your ultimate shortcut to efficient math. Knowing how to apply these to factor crazy expressions or do fast mental math is literally the key to crushing grade 9 algebra.
Before we go, I'm going to leave you with a bit of a brain teaser to test out your new skills. By factoring the expression, can you mathematically prove why n cubed minus n is always divisible by 6 for any natural number n? Here's a quick hint to get you started. Try factoring out the n first and see what identity reveals itself. I'll let you wrestle with that one on your own. Good luck, keep looking for those patterns, and thanks for hanging out with me for this explainer. Stay curious.